Kia ora Year 12 and Year 11. This is a request from Josh for a question from the November 2008 AS paper. Now, it's a really great question and it's got 3 parts to it. And I've just wasted 15 minutes making a video that didn't quite fit all 3 questions in. So I'm going to start again. And in this video, I'm just going to do the first 2 parts. So parts 1 and 2 in here are integration questions, which you'll spot pretty easily. The second one is quite a good volumes of solid question. And the last question is a differentiation question. Now, I want to go through that thoroughly because I think it's important, and so I'm not going to just squish it into the end. The examiner's report for this paper said that this question was pretty badly done, in particular part 3, but I think also part 1 and 2. There are a few little details that you've got to watch out for. So let's go through the first couple of parts of the question before I start. We've got a curve, and the curve is y equals root 3x plus 1, and there are 2 points on that curve. But the shaded region is not just the area under the curve. The shaded region is bounded by the curve, the y-axis, and the line y equals 2. So pretty much as soon as you see it, you should think of a couple of things in here. And the first thing is that when I'm finding the area of this region, I'm going to want to integrate with respect to y and not with respect to x. And that's because instead of finding this area under the curve, what I'm finding is this kind of area under a curve. And so if you tip your head on the side, you'll see that we've got this. The giveaway is that it's got a boundary of the y-axis, not the x-axis. Okay, and then my limits of integration are going to be 2 and 1. So that's the first part. So even that first part, you have to think just a little bit. Although you should, if you're doing 12 MCA especially, have done plenty of practice at integrals where they're tipped over on their side. Now the second part is a volumes of solid thing. And again, this is one where we've got to think a little bit before we do the usual thing. So in an easy volumes of solid problem, we might have limits here of say 2 and 5, and we've got some function f of x. And you can visualize turning around on a pottery urn a piece of wire, right? So if we had a 3D printer and if I was good at that kind of stuff, we could make lots of cool volumes of solids. And what we're doing is we're rotating it like that. And that gives us the formula for our volumes of solid thing, because you can think of each of these as being a very thin disk, which is why it's called the disk method, right? So it's pi times the radius squared, the area of a circle, pi r squared, just like that. Now the difference comes here that we don't have the x-axis as a boundary. What we've got instead is a situation like this one, where I've got this curve and then I've got this other curve underneath it. And I want to find the volume when I rotate that. So the way to think about it is like a washer on a tap, if you guys know what that is. And that's why this is called the washer method. It's nothing to do with washing your face or anything. So here, what we're going to do is to think about, I'm just trying to find a highlighter here. Think about integrating the area under the whole thing, and then we're going to take away this bit here. So it's probably better to think about it as finding the volume of a donut, right? And that helps us find the formula when we've got a question like this. I'm just having pen trouble, as you probably have figured out. So it's going to be pi, and it's going to be the big radius minus the little radius. And once you see that, then this problem is very doable. But the other way to do this one is to notice that instead of having 2 curves, I've got a straight line here. And that means that when I rotate that whole thing, I get a cylinder. And the volume of a cylinder is just pi r squared h. So what I'm going to do, the first way I'm going to do this, is to find the volume of that whole cylinder. And then I'm just going to subtract this easy volumes of solid problem. Right, and I've already been talking for 4 minutes and I haven't really done much maths. Okay, let's get into the algebra. Right, so let's find the area of the shaded region. Well, to do that, I need to turn all of my limits around. So the area is going to equal the integral between 2 and 1 of something with respect to dy. So to do this question, we have to take y equals root 3x plus 1, and we have to change it so that x is the subject. So let's do that. We get y squared is equal to 3x plus 1. And that gives us x is equal to y squared minus 1, all divided by 3. We know that we'll be integrating, so we're going to clean that up and write it like that. So that gives us the area is equal to the integral between 2 and 1 of 1/3 y squared minus 1/3 integrated with respect to y. So we have 1/9 y cubed minus 1/3 y. And now we evaluate the limits. So we get 8/9 minus 2/3 minus, let's see, minus 1/9 minus 1/3. I think that's right. So that gives us 7/9 minus 2/3 plus 1/3. 7/9 minus 1/3 gives us 4/9. So that's my answer for the first part. That's the area. And we weren't given units, so it's just units squared. And now we're going to do this volume of solid 1. Okay, so the first thing I'm going to do again is to write down that the volume is equal to the volume of the cylinder minus, I'm going to call it V purple. Now the volume of the cylinder is pi r squared h. So volume of the cylinder is pi r squared h. I'll just take away that purple for now. So we can think of this here. This is my radius, right? The cylinder's formed, it's a big cylinder, and the height is 1. So it's going to equal pi times 2 squared times 1, which is 4 pi. Now what about the volume of the purple bit? Well, that's not too tricky. And it's not too tricky because we've got y is equal to the square root of 3x plus 1. We need to square that for the r squared part of my volume. So V purple is equal to pi times the integral between 1 and 0 of 3x squared plus 1 dx. Okay, so just going over that one more time, that's because the volume of a solid is equal to pi times the integral of fx squared dx. Now I've made a mistake in there, I just need to erase that squared before someone tells me. So working this out now gives me pi times this, 3 over 2 x squared plus x, evaluated at 1 and 0. That gives me pi times 3 over 2 plus 1 minus 0 plus 0. Remember, always check your lower limit, even if it's 0, especially when you're dealing with trig integrals for people in 13 MCA. So here that gives me 5 pi on 2. So my total area, my total volume is equal to the cylinder volume minus the purple volume under that curve. So that's 4 pi minus 5 pi on 2, which is, what do we get, 3 pi on 2. Now the other way that you could do that, if you didn't like the cylinder method and you just want to apply the washer method, you'll see that you get exactly the same answer. So we'd have volume is equal to pi times the radius of the top line, which is 2 squared, minus this. And when you work that through, of course, you'll get to 3 pi on 2. Now, I just want to talk about a really common mistake that people make when they do the washer method so that you guys can never, ever do that mistake, right? So this is how we want to do it, where we've got the radius squared minus the radius squared. So a very common error is this. I don't even really want to write it down, but I'm going to. So we write down r, the big minus the little, and then we square that. So don't do that. Now, I haven't got time in here, and I haven't got a good 3D GeoGebra set up on my home laptop to show you why those two things are going to give you different volumes. But if you're interested, you can, if you go and Google 3D applets for volumes of solids, washer method, you should be able to find something. Okay, so I'm going to do a separate video to do the tangent question, and it's 8:20 on Friday night, so I'm going to stop now and do that one tomorrow morning. So hopefully this helps you get started on this question, and you can have a go at part 3 on your own.